Okay, so in our last video, we got here. So we were saying that the time of coalescence, assuming that the two individuals randomly picked are from different subdivisions, came out to this. So we can actually, if we multiply this out, we get a little bit more insight. So that just is m plus c over cm plus 1 over m plus 1 over c plus 1 over m plus c, which we can rewrite as 2m plus c over cm plus 1 over m plus c. Okay, so this is not the most intuitive answer. This is not 1 over n. But I just want to point out that we can make some sense of it. So let's take some extreme cases. So one case would be that actually migration is so fast that it doesn't matter. That migration is happening if migration is happening much faster than the coalescent, then what happens there? So if migration is much greater than c, then this value, so that means m plus c is basically m, because c is so much smaller. So then the top of this would be 2m divided by c times m, which we can simplify, and it would just be 2 over c. And then this would be 1 over the mutation rate. So if the mutation rate is, not the mutation rate, the migration rate. If the migration rate, let's say it's 1, that every generation, basically things are swapping back and forth, then we get this. Okay, so if migration is very high, now basically we're back down to no population subdivision. So then what are we looking at here? Well, this is just one generation, which is tiny relative to coalescent time, right? And actually this one generation can be interpreted as the time necessary to get the two things in the same subpopulation, because they started in different ones. And if m is 1, then that happens every generation. It's a little bit weird to think about that because we've made assumptions that m is small. So now when we relax those assumptions, we get weirdnesses. But anyway, this is a tiny value. And then 2 over c. Well, what's 2 over c? Well, we said c was the coalescent, the time of coalescence, time that it takes for two individuals in the same population to coalesce. And we said that that was equal to 1 over, was equal to 2 over n, right? Because it was 1 over n, 1 over n divided by 2. So then if we take 2 divided by c, then we get 2 divided by n, which is equal to n. So we get this value plus 1, which is equal to n plus 1. So what have we just said? We've said if migration is very high, then this somewhat convoluted expression simplifies to n plus 1. So the time to coalescence is n, which is what's expected if there's no population subdivision, right? So when we have high migration, then when we have very high migration, then basically we don't have subdivision, so we'd expect to get the result that we get in a non-subdivided population, and I'll remind you that that is n. So makes sense. When migration goes up, so that it's basically not subdivided, we get our normal old boring result. What about in the other case? What if the rate of coalescence is is much greater than the rate of mutation? Well, then this becomes, so m plus c now is close to c, and so we get 1 over c plus m, we get this value, and then we get 1 over mutation. 1 over migration, because again, c plus m becomes close to c. Okay, so then what is this then? Okay, so now what we have, we can cancel out these c's, and we get 2 over the rate of migration plus 1 over c. So 1 over c is the coalescent time, which is just n over 2, and then so what we see basically is this is the coalescent time within Deems, and this is the bit that's attributable to having to wait for migration 1 or more times. Okay, so this was a little bit rough. My hope here is that in these 25 minutes of videos that you've gotten some practice with sort of working with these things and a little bit more faith that we can relax some of our assumptions and that we can come up with something that kind of makes sense.